Hello. In this session, we will see basic laws in magnetostatics. Today, the session, what we cover is Biot-Savart law. First, we'll see what is the Biot-Savart law. So, Biot-Savart law is an equation which describes the magnetic field generated by constant electric current. It relates the magnetic field to the magnitude, direction, length, and proximity of the electric current. So Biot law is fundamental to magnetostatics, playing a role similar to that of Coulomb's law in electrostatics. So we learned that Coulomb's law and Gauss law and electrostatics. The same way in magnetostatic, we have two fundamental laws. The first one is Biot-Savart law. So in this lesson, we cover what is Biot-Savart law. So here I'm taking that one infinite length conducting infinite length conductor here. So through which current I is flowing. So I'm taking here. So this is the infinite current carrying conductor. So current I is flowing here. In this, we consider a small differential length of conductor. Say it is ideal. So in this part, if I say this is the differential length, so the length is dl. And I want to measure that what is the magnetic field at point P. See here, this is the differential length of conductor. And the magnetic field I am going to measure is, the location is point P here. And now we can make a relation between the dl distance or so distance which connects differential length of the conductor to the point P is r. And the distance r is a vector which is joining point P to the differential length dl. The angle between these two is alpha. As I said earlier, so in Biot-Savart law, the magnetic field is related to the magnitude, direction, and length, and proximity of the electric current. Now we see here, so current flowing through this conductor is I, and we are taking a differential length dl, which is connected to the point P, where we are measuring the magnetic field. The distance is r, the angle is alpha. Now we can define what is Biot-Savart law. So Biot-Savart law states that the differential magnetic field intensity dH produced at a point P, which is shown here, by the differential current element I dl proportional to the product of IDL and the sine of the angle alpha between the element and the line joining point P to the element, that is ideal, and is inversely proportional to the square of the distance r between point P and the element. Let's see detailing. The direction of the magnetic field is always in a plane perpendicular to the line of element and position vector. It is given by the right-hand thumb rule, where the thumb points to the direction of the conventional current I, and the fingers, other fingers, show the magnetic field's directions. For example, if I'm taking, this is my right hand, so this is the direction of current flowing through the conductor, and this is the direction of magnetic field from the conductors. So in this way, which is shown in this figure. Once again, we see that if I'm saying that current is flowing through these directions in the conductor, so this is the current flowing directions I, which is represented by the thumb. And what is the field direction is? Magnetic field direction is in this. So magnetic field is in this way. Now we can understand or we can identify what is the direction of the magnetic field by the two symbols. Here one is a dot, one is a cross. I have shown that in the figure also here. See that the current element is ideal here, and the position is P, and the relating vector R is here. The angle is alpha. If it is so, the magnetic field direction is noted by is the cross. Then what is the meaning of these two directions, dot and a cross? So dot represents that magnetic field is outward, and the cross represents that magnetic field is inward. That means if I take that, this is a current carrying conductor. So current is flowing through upward directions. If a current is flowing upward directions, so magnetic field is in this way. So magnetic field is in this way. So here current is flowing upward directions. So magnetic field is in this direction. That means, so magnetic field is going into the page. Now you are seeing the screen. So if you are seeing the screen, so what is the current direction is through this, and the magnetic field is through this. That is, I say here into the page. That means if you read the text, if you read the textbook, so the magnetic field is going into the textbook, going into the textbook. If I alter the direction of the current, for example, if I'm taking this is a current carrying conductor, and the current flow is in this directions. So current flow is in this directions. That means the current is a downward directions. If a current is a downward directions, that magnetic field will be in opposite directions. So it is coming out from the screen. Now you are watching the screen. So magnetic field is from the screen toward you. So from the screen toward you. That means if you take a textbook, so magnetic field is emerging out from the page of the textbook. That's why a dot is mentioned. So from these notations, dot and cross, we can understand that what is the direction of magnetic field or what is the direction of current flow in the current element. Now, we can write the equations for the Biot Savart law. So what it says is, so differential magnetic field is proportional to the product of current through the current element, that is IDL, and the direction between the, angle between the current element to, so here is a current element DL, the current flow is I. So IDL here, and the position is here. In this point only, we want to measure the DH, because I'm taking the differential length DL, so that so through the differential length, how much current flow makes the proportionally differential magnetic field. That's why we consider here DH. So here DL, here TH. And these two are connected by the radial distance, capital R. And the angle is here alpha. So we can write what is the DH as per Biot Savart law. So DH is proportional to the product of IDL and sinusoidal angle alpha between IDL to the point P. And DH is differential magnetic field is inversely proportional to the square of the distance, that is R square here. Now we can write this equation again. DH is equal to, so K IDL sine alpha divided by R square. Here the K is constant of proportionality. In terms of SI unit, we can write K is equal to 1 divided by 4 pi. So by substitute that proportional constant K value into the equations, now we got DH is equal to differential magnetic field is equal to IDL sine alpha divided by 4 pi R square. So here IDL sine alpha, which is the result of the product. So ideal sine alpha. The previous slide I have shown you the screw directions here. See that? So if you move the screw, it will go upward directions. So here the screw is going upward directions. If you turn it in these directions, if you turn in these directions, so that the rotational screw makes the directions in this way. So here we apply one cross product. So what will be the two parameters in this cross product? So here we take here ideal, so ideal, and one more is vector or. So now I'm taking here. So ideal, so current flow directions and connecting vector AR. So ideal cross AR divided by 4 pi r square. So here this ideal sine alpha can be written as ideal cross AR. So ideal is the current directions and AR is the direction where we are measuring the magnetic field. So the product of these two makes the magnetic field at the point P. So we can write it is again ideal cross, that is unit vector AR is direction of that is the distance connecting the points P to ideal. So ideal cross R divided by 4 pi r cube, because unit vector we can write. So here we can write it is vector divided by magnitude of the vectors. So here we have ideal cross AR. So AR can be written in this. So now it becomes ideal R divided by R, that is a magnitude. So already here we have 4 pi r square, that is magnitude square of the distance. So it becomes ideal cross R divided by 4 pi r cube. So here we have so magnetic field density. So magnetic field is DH is ideal cross R divided by 4 pi r cube. So we can write this, or we can extend this Biot law in different way. That is what we discussed in charge distributions. So in electrostatic, we have seen that charge distributions in different way. That is a point charge distributions, line charge distributions, surface charge distributions, and finally volume charge distributions. The same way here also we have different current distributions, line current, surface current, and volume current. So according to that, we can write this Biot law equations. For example, line current is ideal, surface current distribution is K ds. This is the differential surface area, and the volume current distribution is J and dV. Thus, in terms of distributed current sources, the Biot law can be written in different form. So here it is a DH, it is a differential form. By applying integrations, so H is equal to so integration over this parameters. So now H is equal to, if I take it is a line current distributions, ideal cross AR over 4 pi r square. So here we are taking line current, so that the integration is line integrations. If we take up, it is a surface current. If it is surface current, so in the place of ideal, you are writing K ds cross unit vector over 4 pi r square, and here it is double integration, that means surface integrations. For a volume current, you are writing here triple integrations, that is a volume integrations, and volume current component J dV cross AR over 4 pi r square. Some importance of Biot law. Biot law is similar to Coulomb's law in electrostatics. The law is applicable for very small conductors too, which carry current. The law is applicable for symmetrical current distribution only. So as what we discussed in electrostatics, these were some references. So in the next session, we see what is Ampere's law. Thank you.